Green hydrogen does not scale on technology breakthroughs alone. It scales, or fails, on infrastructure timelines. And the most unforgiving of those timelines is transmission. Electrolyzers can be ordered in months. Renewable plants can be built in 1 to 3 years. But high-voltage transmission expansion routinely takes a decade or more. That mismatch is not a temporary bottleneck. It is a structural ceiling on how large green hydrogen can become in practice. Most hydrogen roadmaps quietly assume that electricity will be available where and when electrolyzers need it. That assumption collapses once you look at the grid as it actually exists. Transmission is not elastic. You cannot reroute gigawatts of clean power on demand just because a hydrogen project reaches financial close. Power flows follow physical constraints, not policy intent. If transmission capacity is saturated, hydrogen does not get special treatment. It gets curtailed, delayed, or stranded. This is why so many hydrogen projects look viable on paper but stall in reality. Developers model electricity prices, electrolyzer efficiency, and incentives in detail, yet treat transmission as a background condition rather than a gating variable. In real systems, transmission determines whether low-cost renewable power can even reach the electrolyzer. Without that connection, all downstream optimization is irrelevant. Transmission expansion is slow because it is not just an engineering problem. It is a permitting problem, a land use problem, a political problem, and often a legal problem. New high-voltage lines cross jurisdictions, trigger environmental reviews, face local opposition, and compete with other grid priorities. Even when a line is approved, construction schedules stretch far beyond the planning horizons used in hydrogen financial models. Hydrogen timelines assume acceleration. Transmission timelines enforce patience. The consequence is geographic mismatch. The best renewable resources are often far from industrial demand centers. Wind and solar can be abundant and cheap in theory, yet unusable for hydrogen if transmission cannot move that power to where electrolyzers are located. Developers respond by siting hydrogen plants near generation instead, but that introduces new problems. Lack of water infrastructure, lack of off-takers, lack of pipelines, and lack of workforce. Transmission constraints do not disappear. They just reappear in different forms. Even when transmission capacity exists, it's usually already fully allocated. Interconnection queues are not waiting rooms, they are bottlenecks. Transmission capacity is allocated years in advance, and hydrogen projects frequently enter the queue late. By the time a hydrogen electrolyzer is ready to operate, the available capacity may be fully subscribed by other loads or generators. The grid does not care that hydrogen is strategic. It cares about reliability and existing commitments. This is where scale breaks. Small pilot projects can often survive on marginal capacity, behind-the-meter arrangements, or temporary curtailment tolerance. Industrial-scale hydrogen cannot. A 100 megawatt or 500 megawatt electrolyzer demands firm, predictable power access. Without transmission expansion, that access does not exist at scale. The system simply cannot absorb hydrogen as a new load without major upgrades. Policy narratives often suggest that hydrogen will help balance the grid by acting as a flexible load. That idea is technically true but economically dangerous. Flexibility is valuable to the grid, but it is costly to hydrogen producers. Every time hydrogen is curtailed to relieve congestion, utilization drops. Capital costs remain fixed. Debt service remains fixed. Flexibility may stabilize the grid, but it destabilizes hydrogen economics. Transmission delays also create timing traps. Developers commit to electrolyzer supply contracts and renewable PPAs years before transmission upgrades are complete. If grid expansion slips, which it often does, the hydrogen plant is forced into partial operation or standby. This period is rarely modeled accurately, yet it can destroy early-year cash flows and violate financing covenants. Hydrogen projects do not fail spectacularly in these moments. They bleed quietly. The problem compounds over time. As more renewables connect to constrained grids, congestion worsens, not improves. prices become more volatile. Curtailment increases. Hydrogen projects that were marginally viable under optimistic assumptions become unviable under real operating conditions. Transmission lag does not just slow scaling, it actively reverses economics. This is why transmission is not a supporting character in the hydrogen story. It is a main character. Without aggressive, coordinated transmission build-out, green hydrogen remains confined to niches, pilot plants, demonstration hubs, and isolated industrial clusters. Those niches are valuable for learning, but they do not constitute scale. Scale requires infrastructure that can move power across regions reliably and affordably. Some regions attempt to bypass this constraint by co-locating generation and hydrogen production. This can work in specific contexts, but it is not a universal solution. Co-location trades transmission risk for other system risks, intermittency exposure, storage dependency, and limited offtake flexibility. These systems can function, but they are brittle. They scale slowly and unevenly. True scale only emerges when hydrogen is integrated into a grid that has excess transmission capacity by design, not by accident. That requires planning transmission for future hydrogen loads before they exist, not after they queue. Historically, grids have been expanded reactively. Hydrogen requires proactive expansion. That shift has not yet occurred at the pace hydrogen advocates assume. At this point in the video, ReneEnergy points viewers to H2 Hub, not as a product pitch, but as a place where hydrogen projects are evaluated through infrastructure readiness, not aspiration. Transmission access, grid timelines, utilization risk, and system stress are treated as core variables. This is the level of analysis required if hydrogen is to move beyond announcements and into execution. The uncomfortable conclusion is simple. If transmission expansion continues to lag, green hydrogen does not gradually scale more slowly. It simply does not scale at all. It remains constrained by geography, politics, and physics. Until transmission is treated as a prerequisite rather than an afterthought, green hydrogen will stay smaller than its ambitions.